In this video, we will take a look at the double angle formulas. This means that we will look at trigonometric functions, particularly the sine, cosine, and tangent functions, evaluated at 2 times alpha. In this warm-up, we are going to correct an error that many students make in a Calculus 1 course. What happens with this 2 inside the argument of our sine function? Can we just pull out the 2, find the sine of pi over 6, and multiply the sine of pi over 6 by 2? In other words, is this the same as this? Well, let's take a look. We know that the sine of 2 times pi over 6 is the same thing as sine of, and 2 times pi over 6 is pi over 3. And the sine of pi over 3 is square root of 3 over 2. Now if we look in part B, we know that the sine of pi over 6 is 1/2. So we have 2 times 1/2, which is 1. And this goes to show that the sine of 2 times theta is not the same thing as 2 times the sine of theta. Or if you're in a Calculus 1 course, you'll often see sine of 2 times x. And that is not the same thing as 2 times the sine of x. Don't make that mistake. So what is the rule? Is there such a rule that can help us with sine of 2 times theta? So let's look at the sine of alpha plus alpha. So we remember that the sine of alpha plus beta equals the sine of alpha cosine of beta plus cosine of alpha sine of beta. So what we're doing is we're replacing beta with alpha. So we have sine of alpha cosine of beta, but beta will get replaced with alpha, plus cosine of alpha sine of beta, but sine of beta gets replaced with alpha. What we have here is the sum of two things that are identical. So that's 2 times sine of alpha cosine of alpha. But alpha plus alpha, that's just 2 alpha. So we've shown that the sine of alpha plus alpha, or the sine of 2 alpha, is 2 sine alpha cosine alpha. Likewise, cosine of alpha plus alpha is cosine of 2 alpha, and that is cosine of alpha cosine of alpha minus sine of alpha sine of alpha, but that's cosine squared of alpha minus sine squared of alpha. Tangent of alpha plus alpha is tangent of alpha plus tangent of alpha over 1 minus tangent of alpha, which is 2 tangent of alpha over 1 minus tangent squared of alpha. So this yields for us more identities to memorize. So sine of 2 theta equals 2 sine theta cosine theta. But now, whenever we look at cosine of 2 theta, this is the one that we saw. Where did these two come from? Well, let's take a look first at cosine squared of theta minus sine squared of theta. Cosine squared of theta is, by the Pythagorean identity, 1 minus sine squared of theta. So we have 1 minus sine squared of theta minus sine squared of theta, and that is our third identity there in the lineup. Well, what about this? how do we get 2 cosine squared of theta minus 1? Likewise, we can replace sine squared of theta with 1 minus cosine squared of theta. So we could take cosine squared of theta minus, and then we will replace sine squared of theta with 1 minus cosine squared of theta. But that is cosine squared of theta minus 1, and distribute that negative, so it'll be plus cosine squared of theta. And that gets us to our second identity there. You should have each one of these 5 identities memorized. So let's apply our double angle identities to this triangle. So something to notice is that this triangle has an angle theta, but our trig functions are being evaluated at 2 theta. So let's go ahead and find the missing side of this triangle by using the Pythagorean theorem. If we do that, we have c squared minus a squared would equal our missing side, a squared. So this would be 40 equals a squared, which would mean that we have 2 square roots of 10 for a. Now, we know that the sine of 2 theta equals 2 times the sine of theta times the cosine of theta. According to our triangle, sine of theta is 2 square roots of 10 over 7. And the cosine of theta is 3/7. So if we multiply this all together, we have 2 times 2 times 3, square roots of 10 over 49. Cosine of 2 theta, we can use any one of the 3 identities. And if we want to avoid the square root here, we can easily use 2 cosine squared of theta minus 1, which will yield 2 times, and now the cosine of theta here is 3/7. So we'll square that and subtract 1. So this gives us 2 times 9 over 49 minus 1. And so this gives us negative 31 over 49. So in the previous example, theta was acute. In this example, theta, however, is between pi over 2 and pi. So let's go ahead and sketch our angle in the appropriate quadrant. And since pi over 2 to pi is the second quadrant, that's why cosine of theta is negative. We can now sketch, this is theta, and we can look at our representative triangle in the second quadrant. Cosine of theta is negative 4 over 5, so our hypotenuse in some sense is 5, and that would mean that our opposite side to this angle is 3. It's a 3, 4, 5 right triangle. So now let's go ahead and evaluate sine of 2 theta. Sine of 2 theta is 2 times the sine of theta, cosine of theta. Again, we don't have information about 2 theta. Our picture is about theta. So 2 times, now what's the sine of theta? According to our picture, it will be 3 over 5. And cosine of theta was given to be negative 4 over 5, or we can see that in our picture as well. And we obtain negative 24/25. Cosine of 2 theta. Well, since we're given cosine of theta, let's use the formula that is dependent only on its value. So 2 cosine squared theta minus 1. So we have 2 times the square of negative 4/5 minus 1. And so this is 7/25. Now we could just take the previous two answers and divide them. However, let's get some practice using our double angle identity for tangent of 2 theta. So 2 times the tangent of theta over 1 minus tangent squared of theta. So this is equal to 2 times, and the tangent of theta is negative 3/4. So 1 minus the square of negative 3/4 is our denominator, which is equal to then negative 3/2 over 7/16. And that reduces to negative 24/7. If we look at the quotient of sine of 2 theta over cosine of 2 theta, negative 24/25 divided by 7/25 does indeed yield the answer we just obtained for tangent of 2 theta. So let's look at how to solve an equation using our double angle identity. So sine of 2 theta can be written as 2 sine of theta cosine of theta. And we've been told that this is to equal cosine of theta. So let's get one side equal to 0. And so that means we're going to subtract cosine of theta from both sides. Now we have a cosine of theta in both terms, so we can factor that out. And now we have two factors whose product is equal to 0. That means either this is equal to 0 or this factor is equal to 0. So cosine of theta is equal to 0, or 2 sine of theta minus 1 is equal to 0. So let's look at each one of those. If we look at cosine of theta is equal to 0, that is a quadrantal angle, and cosine of theta is equal to 0 at these two values. So that means that theta, and we're only looking in 0 to 2 pi, so we can restrict our gaze to simply that interval, and so pi over 2 or 3 pi over 2. If we look at 2 sine of theta minus 1 equals 0, that's the same thing as if sine of theta equals 1/2. So the reference angle there is pi over 6. And that could be in quadrant 1 or quadrant 2. So if we're in quadrant 1, pi over 6 plus 2 pi n, but in this case we're only looking at 0 to 2 pi, so we don't have to worry about the plus 2 pi n. And then quadrant 2, pi over 6 would yield 5 pi over 6 plus 2 pi n, but again we don't have to worry about the plus 2 pi n. So finally we have pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6 as our solutions within the interval. We can also use our double angle identities to manipulate an expression and rewrite it. So if we use our double angle identity for sine of 2x, we can go ahead and rewrite 4 sine x cosine x. But you'll notice what we have here is 4 can be written as 2 times 2. So we can separate the 4. But now, 2 sine x cosine x is our sine of 2x. And we can just bring down the 2. So our answer is simply 2 sine of 2x. And the parentheses are not necessary. It's just for clarity in this situation. So now, if we look at 9 sine 3x cosine 3x, it's a little bit more complicated because 9 isn't so easily separated. So let's force a 2 into this expression. So 9 sine 3x cosine 3x, I'm going to write as 9 times 2 times sine of 3x cosine of 3x. But this is wrong. I've got this extra factor of 2 in front of our sine 3x cosine 3x that was not present in the original. So I'm going to divide the 9 by 2, and then that would balance the additional factor of 2. So now this is 9 halves, and 2 sine 3x cosine 3x is sine of twice the angle. But here our angle is 3x, so twice that would be 6x. In this next example, it almost appears as though we have our double angle identity for cosine of 2 times theta. So let's be guided by that. Cosine of 2x is, in terms of sines, 1 minus 2 sine squared of x. So in this situation, what we need to do is we need to rewrite 10 sine squared of x minus 5 in a different order. So let's write this as negative 5 plus 10 sine squared of x. Now, if we factor out a negative 5 from this expression, what would we be left with? We would have positive 1 minus 2 times sine squared of x, which we've already stated is our double angle formula for cosine of 2x. So this will be negative 5 times cosine of 2x.